Design and testing of a pedestrian footbridge using the finite element method. Bridge design and failure has been studied intensely throughout the structure's history, with many notable tragedies involving bridge collapse. Designs have evolved in an attempt to prevent such catastrophic failures, and with the aid of technology and computational software, testing and modifying a design in a digital environment is safe, easy, and effective. Our project utilized this digital environment to design, analyze, and modify a 16-meter pedestrian footbridge. Our final design utilized a Pratt truss structure made with A36 steel. Over time, and as engineering technology has advanced, bridge designs have begun to account for previous mistakes. Early designs mainly evolved through a process of trial and error until the mid-19th century, when more analytical and regulated approaches to bridge design were required by law. However, generational knowledge continued to impact many newer bridges as designers relied on outdated data. As computers and computing technology progressed, engineers were able to engage in more complicated computations, and the finite element method could be employed in increasingly complex situations where bridge geometry, vehicle models, and nonlinear contact forces evolved throughout the design process. Today, typical footbridge designs include a truss base to support the short-term loads of pedestrian travel across its length, and a cable suspension above the bridge is used to assist in supporting the bridge's weight. When such a bridge is poorly designed, regarding environmental stressors and intended loads, it may collapse, as occurred in 2018 at the Florida International University campus in Miami. The bridge spontaneously collapsed when a critical joint between the truss structure and the bridge's supporting foundation failed, causing the remainder of the truss structure to collapse. Our project sought to document the process of designing, testing, and adjusting a digitally generated footbridge between two buildings, hopefully learning from these tragic mistakes. The footbridge designed was intended to be 16 meters in length and 2 meters wide, spanning the distance between two structures. The bridge was intended to support 50 people, each weighing 70 kilograms, while also remaining intact throughout a Category 5 hurricane. To determine the optimal design for a pedestrian footbridge, we considered the Pratt truss, Warren truss, and Fink truss. The Pratt truss bridge has vertical and diagonal members that point towards the center of the bridge. The truss's geometric properties make it easy, simple, and efficient to design and construct. The Warren truss bridge is made up of equilateral triangles, providing strength and stability while distributing applied forces. The Warren truss maximizes the use of material by ensuring the majority of members share the distributed load, thus reducing the overall cost of material and optimizing the use of labor. The Fink truss consists of web structures in a V shape. Due to its high strength-to-weight ratio, the Fink truss is primarily used as framework for railroad bridges and house roofs. We also studied two materials to develop the bridges. Structural steel was initially used to understand the behavior under different loading conditions in ANSYS. Later, A36 steel was selected for the truss beams as it provides the requisite strength and is lighter than pure iron. The bridges were each designed in ANSYS and used solid circular beams with a 100 millimeter cross-section. After initial load simulations were run, each truss was optimized using the permutations and combinations method. The truss most capable of efficiently managing the given load scenarios was considered the most viable solution for real-world implementation.
To understand the behavior and structural stability of the footbridge, several hand calculations of truss forces and stresses were carried out and are shown in Table 1 and 2. Methods of joints was used to calculate the truss forces, assuming that all the loads and support remain static, that is, the sum of forces in all directions is zero. Stress was calculated using the traditional method of force versus area for each truss member using holotrope cross-section for initial hand calculations. It can be seen from Table 2 that maximum stress in tension is 769.6 kPa, whereas the maximum stress in compression is 820.9 kPa. When designing the footbridge, some initial values and design geometry was assumed based on the given criteria to develop the first model while fixing the corner edges to simulate the bridge between the two buildings. Based on the literature review, 3 bridges were developed in ANSYS with an I-beam cross-section and load of 50 people or 34.3 thousand kilonewtons in negative z direction. The initial analysis used structural steel as a material. We started with an arc bridge as an example and then dived into modeling the initial design of Pratt, Warren and Fink bridge. Here in figure 10 and 12, you can see that the maximum deflection is achieved in the center of the bridge as expected. We will talk about the deformations in all four bridges in the next slide. After the initial analysis was done, it was found that the deflection in arc bridge was 6.23 millimeters, 4.15 millimeters for Pratt Bridge, 3.77 millimeters for Warren Bridge, and 5.23 millimeters for Fink Bridge. As you can see that the Warren Bridge shows the least amount of deflection under crowd loading or load caused by 50 people. But the Warren Bridge has 4 loops as compared to the 2 loops of Pratt Bridge, which has a deflection of 4.15 millimeters. It can be assumed that the Pratt Bridge is much steeper than the Warren Bridge if the loops were increased, and thus it was selected as the final bridge type. After understanding the deflection and stress developed by crowd load, wind loading was introduced to complete the design requirements. The wind speed was first converted to dynamic energy, transforming to pressure applied at the wet surface of the bridge. The pressure was then converted to the applied force just to simplify the loading calculations shown in equation 2. It was assumed that the wind force is applied perpendicular to the walls of the bridge, uniformly with a smooth interaction as shown in figure 13. The area used for calculation is the bridge wall of 16 meters by 3 meters, producing a 144.06 thousand newtons wind load for simplicity of the calculations, which is an overestimate but helps to provide maximum deflection. If the actual area of the contact is calculated, the force acting would be much less, causing less deflection, improving the structure's stability against wind loading.
Now moving on to the design process and load application. After applying the wind load on the new design, the deflection of the members was greater than 78 mm, which can cause the bridge failure. To make the bridge stiffer against the wind load, multiple diagonal truss members were created in the bridge ceiling and the floor section to reduce the major deflection in the top and the bottom members. It can be seen from the figures how the optimization in the bridge design was carried out. After the iterative process of optimizing the design of the bridge, the final design was selected to be a Pratt truss bridge with a solid circular cross section. In order to minimize the material usage, members were given different cross section while providing enough stiffness against different loading conditions. It can be seen in table 3 how the changes in the cross section of different members were made. The vertical diagonal members have an elliptical cross section with a semi-major axis of 100 mm. This design would provide a better flow of wind around the beams when subjected to wind loading. The material used for the initial analysis was structural steel. After researching for a stronger and lighter material, it was found out that A36 steel has better properties than structural steel and would make a strong, sturdy bridge. Table 4 shows that A36 provided to be a better material in all the loading conditions as compared to structural steel, causing less deflection and also low stresses induced in the members. Moving on, the results of our optimization process, figure 16 and 17 show the deflection contours for wind loads for a category 5 hurricane and crowd load of 34.3 kilonewtons. It can be seen from figure 16 that the deflection is maximum in the top members, which is 18.25 mm under wind loading conditions. This can be said to be an acceptable value as it lies within the limiting value of 20 mm. Stress analysis for both the loading condition show some excellent results. Figure 18 and 19 show the stress contours under crowd loading and wind loading conditions respectively. The maximum stress mostly acts at the root of the vertical members which have a greenish tint, whereas the rest of the blue part indicate that very small amount of stress is acting on the rest of the members. To summarize the results, it can be said that an average stress of 100 megapascal acts on the bridge members under wind loading conditions. Table 5 shows the final results of our analysis process. The deformation is 1 mm for crowd loading and 18.25 mm for wind loading conditions, and the maximum stress is 26 megapascals and 100 megapascals respectively when A36 steel is used. In conclusion, it can be said that the circular cross-section provides strength, durability, and feasibility to the structure when combined with A36 steel material. The design and optimization process excludes different other aspects like fatigue, creep, and vibrations, which can be calculated to get an even more detailed design of the bridge. The proposed Pratt truss bridge design can further be made more strong and cost-effective by using hollow cylindrical cross-section. The deflection in Pratt truss bridge using this new cross-section drops down to 4.8 mm under wind loading conditions as depicted in figure 20. This cross-section will help to make the bridge stiff and reduce the material usage, thus contributing to optimizing the cost of the project. It may also lead to lesser stresses getting induced in the members of the structure.
These are some of the references we used for this presentation.